Okay. Good evening, everyone. And those who are joining remotely from another place, good morning, good afternoon, whatever is relevant. So today is our lecture 9. So we're going to cover two of the most important sorting algorithms. One is the merge sort, and another is the quick sort. And we'll take some time to understand these two algorithms. And then we will just briefly introduce the graphs. But before we get into merge sort, quick sort, I just wanted to touch upon one point that I mentioned about heaps. And if you remember, I mentioned that for constructing the heaps, there are two ways of approaching it. One is as the input elements come, you take one by one, and then you perform the heapify operation or satisfying the heap order property one at a time. So then for satisfying the heap order property, it will take you log n time because you are introducing the node or the key or the entry at the end of the array, and you're allowing the array to find a suitable place. So that operation is going to take log n, and if you have n entries, then it's going to be n log n. But we mentioned that the bottom-up heap construction, so construct bottom-up heap, if we approach in a slightly different way, where we have got a collection of entries, we just throw them into the array, and then we, starting from the first or the lowest internal node, and then we keep performing the heapify operation. So which essentially means we are performing for each node in a backward manner. So starting from the lowest internal node, so which is going to be, the position is going to be like, if you have n elements, so it's going to be n by 2. So at the n by 2 position, whatever element is there, you're going backward. So n by 2 to 0. So for this range of indices, you go back and you perform the bubble down operation, which means that you try to find the right place for that particular node. And we said that if we perform the construction of the bottom-up heap using this strategy, then, so this is one entry at a time. And if we take this approach, then the complexity will be just linear. The question is, how is it so? Okay, so we wanted to just prove that point a little bit before we go down to discussing the merge sort, quick sort, and graphs. So we'll come back to these topics after we have covered this. So let's first recap that if you have a complete binary tree, let's be clear about the relationship between the height and the number of nodes. So if you have only one node, then the height is 0, right? And the number of nodes is going to be, number of nodes at this height is going to be, so number of nodes at height h is going to be 2 to the power 0, which is only 1, right? So there is only 1. So if I go to another level, so increase the height, then the number of nodes at height 1, right? So number of nodes at height 1 is going to be 2 to the power 1, right? So I can write down 2 to the power 0. This is 2 to the power 1, which is 2. And you can capture also total nodes at this point. So total nodes here is 1. And we expressed that, you can express that as 2 to the power 0, which is the height, plus 1 minus 1, right? So we said that generally when we want to see the relationship between n and height is 2 to the power h plus 1 minus 1. Okay, so let's increase a little bit more just so that the point is clear. So here you can see the same way, the total number of nodes at this height is equal to 3, right? So 1 plus 2, 3, or you can see it as 2 to the power 1 plus 1, which is 4 minus 1 equal to 3. Okay, so let's just see one more level. So if height equal to 2, then the number of nodes at this height you can clearly see is 2 to the power 2 equal to 4. Okay. The total number of nodes so far is, you can see 1 plus 2 plus 4, which is 7, but we can also see it like that, height plus 1, which is 2 plus 1, which is 8 minus 1, which is equal to 7. And in this way we can generalize. So at height h, the number of nodes will be 2 to the power h, right? And likewise, the total number of nodes will be 2 to the power h plus 1 minus 1. I hope this point is clear, okay, before we even enter into trying to understand the proof for this point. Any questions so far? Okay.
Wait, sorry. Could you clarify the lowest internal node again? This is backtracking a bit, but could you clarify that?
So in this particular complete binary tree, right, what is the lowest internal node? These 4 nodes are all leaf nodes, right? So this is going to be the lowest internal node. So there are 1, 2, 3, 4, 5, 6, 7 nodes, right? So 7 divided by 2, which is the third, right? So that's why I said it is n by 2. That's the index. Is that clear? This is the lowest internal node.
Yeah, so it goes root nodes 1, and then 2 is the left node, and then 3. Like that.
Right? You see the index of this, right? Which is 7. 7 divided by 2, that gives you 3. So 1, 2, 3.
Okay, makes sense.
All right. So for applying the bubble down operation, we start from here and we described how we are going backward from here, right? We start from n by 2 and we are going backward until we reach the root level node. So when we are going backward, so that many bubble down operation would be there. So we want to see when we sum up all of these, we will end up in order of n. That's what we want to prove here. Okay. Okay. So let's try to keep going. Okay. So what is the overall number of operations that would be involved here? So it's going to be sum of the heights of all the nodes Why is it the sum of the heights of all the nodes? So remember, height is from the bottom, right? Depth is from the top, height is from the bottom, right? Because with respect to this node, like when we are performing, pointer, okay. Okay, just hold on, I'm getting the connection back. Okay, it's back. Okay, so when we are looking at this node, so when we are performing bubble down operation, right? So it's whatever operation is getting performed, it is kind of with respect to the height of this node, because we are trying to find the appropriate place downward for this particular node. So therefore, as we are going through performing bubble down operation for each of the nodes backward, therefore, the number of operations that we're going to perform is going to be proportional to the sum of the heights of all the nodes, because in the worst case, it is going to span the height with respect to this node. Is this point clear? Because this is the basis for showing the proof.
Wait, sorry, could you, I'm still confused about the part where you say like,
let me just
you add from the back or something. Could you clarify that?
let me just draw and because it's a complete heap, so it's going to be maybe at this position. Okay. So now the lowest internal node, sorry about that, my device is giving me trouble. All right, so the lowest internal node is going to be this, right? So from this internal node, we are going backward until we reach the height, right? Reach the root. So at every step, we are trying to find what is the position downward for this. Because remember, we have just placed the keys arbitrarily within the array. So we want to find out, can it go down here? So by comparing, we see if this value is greater than this, then this should be swapped with this, right? So for this node, only this much is the mobility of this node. Okay, I need to pause this because I need to connect another device. This is kind of getting jerky right now. Just give me 1 minute, okay? I need to replace. Okay, are you able to hear me still? Just wanted to double check.
Yeah.
Okay. All right. So from here, the amount of possible path that it has to traverse to find its right position is just one level down for this node, right? For this node, likewise, it's only one level down. So it's that much is the height. For this node, likewise, only one level down. Now coming back to this node can find its position from here to here, and then again it can find here. So how much it has to travel in the worst case, it is the height of that node. Is this point clear for the bubble down operation? Any question on this point? Because when we are talking about bubble down operation, we are just trying to find the right place for that node downward. And we are going backward from here. So for every node, it is getting an opportunity to find its right place, traversing through the height at which that node is currently there. Any question on this? And that is why the number of operations is going to be the sum of the heights of all the nodes. Because for every operation, it is going to perform that many bubble down operation. Question.
So just to clarify, the worst case is like for a given node, I guess the height or the number of walks it takes to get to the bottom leaf node, basically.
Yeah, in the worst case, I mean, it can settle down even before reaching the bottom, but in the worst case, it may need to travel to the leaf node. That's the point. Okay. Okay, so now, so let the height of the complete binary tree equal to h. Okay, because it's a complete binary tree in the worst case, right? For a heap, which means that it is completely filled up. Okay, so how many nodes are going to be there at depth? So at depth I, so depth I is from the top.
Two to the I plus 1 minus 1.
So at the depth I, so for just now we established these points. Actually, I'm really sorry. Here is where I meant, let's call it depth, because this is from the top. I don't know why I was writing height. Right, so this should have been, because this is from the top, right? This is D. Really sorry. I hope I did not confuse you on this one. Because as I said, like height is from the bottom, depth is from the top, okay? So let's just call this D. Okay, any question on this point first? Because we were looking from the top, right? Sorry, can you repeat again what you just said? Because I just detected that problem and wanted to correct that. Can you repeat that, what you just said?
2 to the I plus 1 minus 1.
So at depth I, right? So based on this, you saw, right? How many nodes are going to be there? That's the first question we want to say. So number of nodes.
Two to the power of I.
Exactly. So number of nodes equal to 2 to the power of I, right? My device is not cooperating. I'm really sorry. I don't know why it is getting turned off again and again. Okay, let's see whether this works better, because I just changed the port. There is something problematic going on with my device today. All right, so at depth I, number of nodes is 2 to the power I, okay? Okay, next question. What is the height of a node? What is the height of a node at depth I? So remember, this whole thing is the height is, as you remember, it's in terms of the edges, right? So this is the height of the overall binary tree representing the heap, right? Now we are asking, what is the height of a node at depth I?
H minus I.
H minus I, exactly. Okay. Somehow my device is getting reset again and again. I'm really, really sorry. Let's see. Sum of the heights of okay, let me take one more pause. Sorry. Just okay, let me just see what happens. Okay, so sum of the heights of all the nodes at depth I. So what is going to be the sum of the heights of all the nodes at depth I? So if you take a depth of I for this node, right? So this is the height. So this is the sorry, this is the depth. And this is H minus I, right? So if you take a node, so what would be the sum of the heights of all the nodes at depth I? It's going to be, so height of each node is H minus I, right? So it's going to be H minus I plus H minus I plus H minus I. As many nodes are there at that level, right? So which is, we know that there are 2 to the power I nodes, correct? So it's going to be 2 to the power I times H minus I. Is this point clear? Therefore, the sum of the heights.
Yeah.
Yeah, please go ahead. Question?
No, it wasn't a question. It was just saying
Okay.
that, yes, you're very clear.
Okay. So now, therefore, sum of the heights for all the nodes now. So not just at that depth, for all the nodes. How are we going to find out? So we take 2 to the power I times H minus I. And we now have to sum over all the nodes, right? So all the nodes which are spanning the overall height, right? So here, so at depth I, so the depth I can span from 0 until H, right? So this is going to be the overall sum of all the nodes, the heights of all the nodes. So let's say this is S, okay? Because we need to find out the value of this. So we can write down S is equal to, so let's say I equal to 0, then it's 2 to the power 0, which is 1, right? Times H, right? H minus 0. So that is H plus 2 to the power 1 times H minus 1 plus 2 square times H minus 2 plus dot 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 plus, when the value is H, then this expression is 0. So we have to reach 2 to the power H minus 1, in which case H minus 1 is going to be equal to 1. So it is 2 to the power H minus 1 is going to be the last term. So how do we evaluate the sum of this? So we can apply a trick here. We can do 2 times S here, and we shift this. So this is going to be 2 times H, right? Plus 2 times 2 times h minus 1. That's going to be 2 square times h minus 1 plus dot dot dot. The last term is going to be 2 to the power h because it's multiplied by 2. All right. So we now subtract this one, the first one from the second one. Then we will get s here. Okay. This is going to be 0 plus, right? So this is 0 minus h, which is minus h, plus 2 times h minus 1, which is 2, plus 2 square times h minus 1 minus h minus 2, which is 2 square. So you can see this is going to form the series of 2 until 2 to the power h as the last term. Okay. So now we know how to calculate this. This is just a geometric series. So you can say minus h plus 2 times 1 plus 2 plus 2 square plus dot 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 plus 2 to the power h minus 1, right? So this is equal to minus h plus 2 times 2 to the power h minus 1, right? That is the formula for computing this sum. All right. So having obtained this, we already showed that if the number of nodes equal to n, right, then n is actually equal to 2 to the power h plus 1 minus 1, right? That's what we showed here, right? So here, in this case, height is equal to the depth, right, for the whole tree. So 2 to the power height plus 1 minus 1, correct? So now, if that is clear, so this is what? Minus h plus 2 to the power h plus 1, like if we just expand this much, minus 2 once we distribute 2. Now we know 2 to the power h plus 1 is n plus 1, right? So 2 to the power h plus 1 is equal to n plus 1. So then we can say this is minus h plus n plus 1 minus 2, right? So what do we get from here? It is n minus h minus 1. So what is the dominating term here? It is n, because this is order of log n, right? So then therefore this is order of n. So that's why the overall number of operations that are getting performed for bottom-up heap construction is order of n. Any question? Okay, so we'll